So now we have the last one. Hang in there, don't fall asleep. One more. Rüdiger.
Yeah, last presentation, just another 15 minutes for you. Today we heard a lot of presentations about the application of Hydrus for soils. And for some beautiful things in life, this is not enough to look at soil. So if you look at this very beautiful flower, if you want to put it in your living room, you have no chances if you use soils, but you have to use growing media. My name is Anlauf. I work at Osnabrück University of Applied Sciences, and where I work it's the Department of Horticulture, and that's why I'm interested in using Hydrus to describe water and gas transport in growing media. If you look at growing media, oxygen is one of the biggest problems we have to deal with, and the usual parameter where the quality of growing media for oxygen supply is used for is the air capacity. Air capacity is, well, you know it from soils. When we look at talk about growing media, the air capacity is the air content at container capacity. And container capacity, again, is something very similar to field capacity, but it's defined at the water content at a suction of 10 hectopascal or 10 centimeter water current. And if you buy growing media and if you look at the back of the bags, mostly the producers put the figure of this air capacity there. And there are, well, a lot of figures that tell you that if the air capacity is more than 10%, this should be sufficient for most plants you will grow, and if it's less, you may get problems. Now, but if we look at the horticultural practice, if we talk to horticultural producers, there are a lot of examples that producers use poor growing media with low air content, but they have good results, and other producers use very good growing media with relatively high air contents, but they have problems with oxygen supply to their plants. And the reason will be that this air capacity is a very, very static parameter. And of course, if we look at irrigation and all the other things, we need a dynamic system. And we think that, or we expect that a dynamic system can be described with simulation models. So this is the background. Now, the objectives of our investigations we did in the last years was first to describe the physical parameters related to water and gas transport in growing media. And growing media, we have a wide range of different growing media, different compositions, different densities, and so on. Then we used Hydrus to describe water uptake and redistribution in growing media. This is the only thing I want to talk about today. We want to use a bit later Hydrus 1D to simulate oxygen movement and supply in growing media, and the final goal is that we want to develop a system which should be easily but correct enough to be used for growing media, for producers of horticultural products. Now, just one example, ebb-and-flow irrigation. This is a very common irrigation system in in horticultural systems. That means you flood the area for something like 5 to 10 minutes, and then you drain it again. And this could be used on tables, it could be also used on concrete floors, like in this example. And if you talk to the farmers who use it, they say, okay, we often have problems at the edges where it's too dry. We measured some results or some examples there. And for example, here we had a flooding depth of 0.5 centimeters for 10 minutes only, because there's a slight slope on these concrete grounds. And in the center, we measured a flooding depth of 3 centimeters for 15 minutes, and the farmer complained that the ridge was often too wet and not enough oxygen. So, just two examples for growing media. These are the growing media we used. This is a standard white peat or light peat, less decomposed, and this is the like 80 or 70% of the growing media which I use consists of this white peat. And then a seedling substrate is much, much finer. It contains white peat, but also black peat and some other fine material. And this is used for sowing plants or for putting very young plants and small plants there. Now some properties, if you look at the bulk density, it is 0.3 or 0.13 or 0.14 gram per cubic centimeter. Of course, much, much lighter than mineral soils, less weight than mineral soils. Then particle density, something like 1.6, and we have 2.6, 2.7 for mineral soils, also much lighter. And the reason is, of course, the high organic matter content. Most of the growing media have organic matter content above 0.8 gram per gram. Now, there are also some very distinct differences if we look at the physical parameters. Total porosity, 0.91 for the seedling substrate and 0.92 for the white peat. Much, much higher pore volume compared to mineral soils. Then the air capacity, what I talked about, is 0.21 cubic centimeter per cubic centimeter for the white peat and 0.03 for the seedling substrates. And many farmers who use these would say, well, this is too much to grow normal plants there. And then if we look at the particle distribution of these two examples, we calculate the mean weight diameter, and you see for the seedling substrate it's a bit more than 1 millimeter, and for the white peat it's nearly 6 millimeters, so coarse and a very fine example. Then we use standard laboratory equipment to determine the water retention curves and the van-Genuchten parameters. I don't want to go into these details. We determine the air entry value, and then you can calculate the air entry value to pore diameter, and we calculated 3 millimeters for the largest pore in the white peat and 0.4 for the seedling substrate. And if you look at it in more detail, just visually, this should be correct, these values. Now, if we want to use it for Hydrus, we need initial conditions, and these are the initial conditions we use. This is the pot from the surface down to 10 centimeters, so a 10 centimeter high plant container. We started with the magic potential, which we measured under the conditions where we received the material, which is about 20 hectopascal or 32 volume percent for the fine substrate and about 5,000 hectopascal for the white peat. So this is the initial conditions down to the place where the water surface during flooding is. Now we have two examples, 4 centimeter flooding depths and 1 centimeter flooding depths, and for practical conditions mostly it's between 2 and 3.5 centimeters. So that means if we look at this curve, 4 centimeter flooding depths, we have a potential of 0, a constant head of 0 at 4 centimeter, well, height above the surface, the bottom end of the container, and we have a height of plus 4 centimeters or hectopascal at the lower end of at the bottom of the container. Well, these are the initial conditions, and if we look at the boundary conditions, we have two phases. First the flooding phase and then the drainage phase, and of course we have to change boundary conditions. In the flooding phase, we have the lower boundary condition, this constant head I said before, and then we simulate capillary rise in the growing media. And then after these 10 minutes or 5 to 15 minutes, we have to change the boundary condition, because then we have the drainage phase, and then we have the seepage phase at the lower end of the profile, and we simulate both further capillary rise into the rather dry media above and drainage from the growing media. When we started with these investigations, we used small containers and we put in small tensiometers, but we had a lot of technical problems with getting contact in these very soft material. Then we bought small FDR sensors, which worked also not very good because there's some influence between these sensors if you put them too close together. And then finally we said back to the roots. We constructed these very simple containers. They consist of rings 2 centimeters high, and then we just made our experiments. and then we cut the containers and just oven dried the material to get the water content. A bit untechnical and unsophisticated, but it works really nicely. Well, this is the experimental setup. And then we put everything, or the first results, into Hydrus, and then, well, we had a look at the results. Looked very disappointing. Let's have a look at the white peat. These are so this is the container from the top to the bottom. This is the water content. These are the results from Hydrus 1D. And these are the measured results, and Hydrus gave us much too high water contents in the containers, very similar to the seedling substrates. So there is a much overestimation of capillary rise in the growing media, and very poor simulation quality, and we think that hysteresis is the reason. So we're starting measuring hysteresis of the water retention curve for this growing media, and again we try to make it a bit simple. So this is our container again with these 2 centimeter rings we put in the growing media. Then we apply the flooding depth of 1 centimeter, and after equilibration we should expect tension of -2 hectopascal and 2 centimeters above the surface, and so on. Then again we cut the rings and measured the water content and could use this as an aid to estimate hysteresis. Then we put, this is the drying curve, and these are the results of this very simple way to measure hysteresis. Then we applied this to an optimization program. We changed the alpha parameter of the van-Genuchten curve, and then we have the wetting curve and the drying curve for both parameters. These are the results, and I just want to show you the relation of both. And if you look at the literature, for mineral soils, mostly they say it should be something about 2 or so. And here we we have results about 6 or about 7, and we used some other growing media, and we had similar results. So that must be the reason of the completely different pore system in this growing media. Then again we use Hydrus with hysteresis and the changing alpha, and well, great success. It's looked very nice for the white peat, and it looked relatively nice for the seedling substrate. So the result is that the water uptake is much less due to hysteresis, and that must be if you look at growing media. And we had relatively good simulation quality. This is again plot simulated minus against measured, and we had high correlation coefficients for the water content which we measured. Simulation quality, mesh subcliffe, I think you know about that, very often used from hydrologists, something like 0.84 to 0.97 for these seedling substrates, and 0.7 to 0.8 for the white peat, and a slope slightly more than 1, indicating that there's some overestimation for the high values and some underestimation for the low values. So this is for water content, and this is the same for water uptake into the containers, because this is something where the producers are much more interested in than the water content distribution. And again, we have relatively good simulation quality. I don't want to read the figures now, but you can have some impression with these figures. Now, if I do some conclusions and summary from this part of water movement. So growing media show strong hysteresis. This is known, this is nothing really new, but if we want to simulate it, we have to take it into account somehow, no chance to do it without. Hydrus 1D is able to describe water uptake and redistribution under Ebb-and-Flow Irrigation systems sufficiently well. Possible reasons could be the description of this hysteresis that have to be investigated more in detail also. And we think that Hydrus 1D is a promising tool to overcome this pure static description of this air capacity parameter towards a dynamic description of water movement. Now, but my main interest interest is not in the water content, but in oxygen supply in growing media, because this is the main problem for the people who practice or work with them. So we did some further work. I cannot give any detail or any results now, but we measured and modeled the dependency of oxygen diffusion coefficient on air content for different growing media, different bulk densities. That's the big problem. If you have different farmers, they all use different bulk densities for the same growing media. So this is what we measured in diffusion chambers. Then another point very important for simulation of oxygen later will be oxygen consumption in different growing media, depending on different fertilizer status and so on. So this we did with Isermeyer method, that's a method from soil biology. And then we measured oxygen concentration profiles under very many different oxygen, different irrigation situations. And we used optical O2 sensors, so we have a lot of data now. And the last step we have to do is well, the oxygen simulations with Hydrus. So we have to make some slight changes on the source code, and we started with that already, but there are no results I can present. Okay, and because this is a well, workshop, and I know that there are very few people working with growing media and simulation models. And I'm really very much interested in contacts with colleagues who work with growing media. There are so many people using Hydrus for soils, but growing media is, when you look at the situation in Germany, it's such a big economic thing. You can make a lot of money with growing media, and I think this is the same in other countries. So it's really an important thing. So if somebody is interested in that, I would be really interested in getting contact. Okay, thank you very much.
Many of the flower growers in Holland,
yeah, rock wool is used mostly for vegetables, but for ornamental plants usually it's a growing media, because they are sold after 6 weeks, and at home you don't want this rock wool. There's one question over there.
One concern that arose when I was thinking about the growing media. That comes into my mind is that of publicity. Did you think about these things?
Could be a problem, that's right, but only if they get very dry. And usually they cannot getting dry, because then the plants will die. So usually they will never, under normal conditions, they will never get very dry. And then hydrophobicity should be not a big problem. Sometimes the producers of growing media add also some chemicals to prevent hydrophobicity.
but it would add to that alpha wet, alpha dry ratio. I would agree.
Yeah. Please, is this the only way to irrigate these spots? They cannot irrigate it by dripping or by micro sprinklers or whatever?
Of course. They did in former times, they used sprinklers, but then they have a lot of problems with phyto problems.
Fungi.
Yeah. Or they use these spaghettis, they're called in German. But if you have, like in this photograph, where you have thousands of pots, you cannot do it by hand. It's much too, well, maybe in other countries, but not in Germany. It's simply too expensive. So this is the very, very usual way to use Ebb-and-Flow irrigation.
It's very nice, because when you harvest, you can expand.
No, but you can make fixed dripper lines. They can drip.
If you have thousands of pots,
it's
much too much labor and work. It's much easier.
Thank you very much.
So thanks again, Rüdiger. So I guess this is it. We're going to have a little coffee break, and then we have a poster session. I don't know.